Okay, so a couple of comments about today. Today sucks. I mean, honestly, I'm worried about myself and all my screw-ups for today because this is a very, very technical subject that we're going to talk about today. However, at the end of it, there will sort of be some, hopefully some insight into something which I know you all have heard of. That's called the stress energy tensor. And what we're going to do is we're going to give that a real solid definition today. We might or might not finish it all today. We might have to do a little bit on Tuesday. But what I can tell you is that what we're predominantly going to talk about on Tuesday, you will rather enjoy. Okay? So just keep that light at the end of the tunnel. We just got to get through this hardcore stuff today. And once we get to what we're going to talk about next Tuesday, which is really where we're going to start going into general relativity, by the way. But it's going to be a very conceptual-oriented topic. So to get started today, I got to finish up with a couple of comments. So first of all, oh shoot. I copied something down from my notes on the board last time, which I want to correct. And I want to send out gratitude. Yes?
The link to submit our assignments on Canvas isn't open yet.
I think it'll be open at 5:30, so just hang on to the assignment and enter it at 5:30.
Okay, thanks.
Turn him down. I'm not going to do anything. Nope. There we go. Say something, Ross. Oh, nice. I'm just kidding. I want to send out thanks to Muttley, who made this correction for me in a comment to the video. So thank you, Muttley. But so I had this in matrix formulation written as H goes to H prime. And I had that as lambda H, lambda inverse transpose, when in reality I shouldn't have done the transpose. So if anybody was really paying attention to my switch from index notation to matrix notation, you might have realized that the last lambda inverse did not have to be transposed. So that's one correction. Another correction, though, feeds a little bit more into today, and that is when we are starting to talk about dynamics and kinematics. Okay, I wrote down the definition of tau as the integral of the square root of ds squared. I would largely ignore that. I wouldn't even pay attention to that. What we want to do is we want to focus on the following expression. D tau squared is minus ds squared, okay? Now that looks weird because it's two things which are squared and there's a negative sign relating them. So how the F does that work? Because shouldn't this be positive? Shouldn't this be positive? But remember, these aren't just numbers. This is the magnitude of a space-time vector, which is ds squared is minus c squared dt squared plus dx squared plus dy squared plus dz squared. And this can be negative, positive, or even zero. Okay, so ds squared, just because it's squared doesn't mean it's always positive. And what we observed last time is for anything that's traveling less than the speed of light, which is going to be pretty much everything we're interested in this course, except for light itself. But anything that's traveling less than the speed of light, ds squared is negative. So we're going to define the parameterization in terms of d tau squared, which is minus ds squared. That way this thing is just a positive parameter. Okay? So I wanted to clarify that. And what we ended on last time was the definition of the four velocity as u mu is dx mu d tau, where recall the reason we have d tau here instead of dt is because if this was dt, then the numerator would transform like a vector, but dt transforms like a component of a vector. So this thing on the right is not actually a vector. You can't take a vector and divide it by a component of a vector and expect that the result is a vector. So we found this d tau, and this is an invariant. Okay, it's defined as, I mean, you can define it in terms of the square root of minus ds squared, but at any rate, ds squared is an invariant, so d tau is an invariant. So if this is an invariant and this is a vector, this is a vector. Okay? Now, also I finished with the observation that the square of any four velocity vector, which is just dx mu d tau, dx mu d tau. Well, this is just eta mu dx mu dx mu d tau squared. But remember, d tau squared is minus eta mu nu. Or sorry, minus ds squared. Sorry, I can't talk and write at the same time, so I'm just going to shut up and write. This is minus ds squared, but minus ds squared is exactly what's in the numerator. Remember, it's minus c squared t squared plus dx squared plus dy squared plus dz squared. That's exactly what the numerator is. That's why this comes out to minus 1. Okay? Just wanted to clarify on that. All right? And I gave you a little argument for why the square of the four velocity always being a constant makes sense, because we're parametrizing the path in terms of the length of the path. Okay? Now, I want to make a brief announcement. That is, from here on out, we're going to natural units. And in natural units, what is the speed of light? 1. So I will drop the speed of light. I won't write c anymore. Okay? At the end of a calculation, if you need to go and plug in numbers, which you'll rarely do, but if you need to plug in numbers, you just put a c wherever you need a c. So for example, if you've got a gamma, clearly there's only one way to fix that with c, and that's to make this v squared over c squared, because we've got a dimensionless number, we need this to be dimensionless, so you fix that with c, okay? But at any rate, it shouldn't play too much of a role in what we're going to do. All right, so now what I want to talk about are the components of this four velocity, okay? Remember, we said, you know, we're going to go from 3 dimensions to 4 dimensions, so every vector has to become a 4 vector. We took the velocity vector and we asked, what's the 4 component velocity vector? And we said we were going to define it with this, but let's see if we can explore what the components of this are. So here we go. So we first of all have the u0 component. And remember, this is a function of tau. Tau is the thing that is parametrizing this. So if we're going to write it as a function of anything, we should write it as a function of tau. This is just dx0 d tau. I just say mu is 0. That's it. Okay? But dx0 is the first coordinate. That would have been ct before, but now it's just t, because c is 1. So this is dt d tau, okay? But remember, I can write dt in any frame in terms of gamma times dt in the rest frame, where the gamma involves the velocity, which relates the rest frame to the frame I'm defining dt in, or t in, okay? Oh, wait a minute. What is dt rest?
D tau.
It's d tau. Holy crap. The first component of the four velocity vector is just gamma. Gamma is 1 over the square root of 1 minus v squared. Okay, I don't know why I erased it. Now let's look at a spatial part. And we're going to cheat a little bit here. dxi d tau, where I can be 1, 2, 3, or xyz if you prefer. Well, let's just cheat a bit. Let's call this dxi dt times dt d tau. Hey, What is this? Hold on. Drew. Drew? Drew. I can't recognize you with pink hair. What is this?
Gamma.
Yeah, that's gamma. What is this?
Velocity of the original frame.
Yeah, so we could write this as VI times gamma. There you go, folks. So in the end, putting this together, U mu has components gamma, gamma, V. I want. Say it again. Huh?
Is this not pink enough?
Well, yeah, no, that's a good point. I mean, it almost matches your hair. Okay, anyway. Notice, this is not just taking the velocity as a 3-vector and then adding a time-like component to it. It's actually multiplying the velocity 3-vector itself by gamma. So the modification to get this to be a 4-component vector is more than just adding a time-like piece to it. All right? Now, notice, if I take this form of U mu and I do this, remember to lower the index here, I'm just going to apply the metric to this, which is just going to make this term negative. So at the end of the day, this comes out to minus gamma squared plus gamma squared V squared. Anybody recognize that? It's minus 1, as expected. Okay, if you just plug in gamma squared here, that'll simplify to minus 1, as promised. Okay? What about in the rest frame? Skylar. Skylar here? Skylar. What is the form of the 4 velocity in the rest frame? What is that in the rest frame?
Oh, so gamma then zeros.
Say it again?
In the rest frame, is it gamma then followed by zeros?
Well, what's gamma in the rest frame?
Oh, which is zero.
No. Remember, gamma is 1 over the root of 1 minus v squared, square root. So what is gamma in the rest frame? 1. Okay? Hey, look at this. If I do U mu, the dual vector gets a minus times the original vector, minus 1, as promised. Okay? All right. There's no way in hell I'm going to get through all this material today, but that's all right. Okay, so we have basically covered kinematics. We've defined the position vector, the velocity vector. Now let's turn to an element of the dynamics, and that is the momentum. Okay? The momentum is going to play a very important role in what's coming next. So for momentum, we can give a definition as the momentum 4 vector is the mass times the 4 velocity. Okay? It's kind of using the same definition we use in non-relativistic physics, where we say the momentum is the mass times the spatial velocity. Okay, we're taking this by analogy. Turns out this is a perfectly fine definition of 4 momentum. This is a vector because the mass of something is invariant. You might have taken a special relativity course at some point where they said mass scales with your velocity. That's crap. Don't pay attention to it, please. Mass is an invariant. So this transforms like a vector, therefore this transforms like a vector. This is a vector, okay? Of course, its components are just going to be the mass times gamma and the mass times gamma times the velocity. That's just using the components of the 4 velocity. And now we can do something rather interesting. We can say if v squared is much, much less than 1, which is secretly c squared, of course, that is, if we're traveling less than the speed of light. Then we can expand gamma, okay, which appears in both of these terms into the following form: 1 plus 1/2 v squared plus dot dot dot. Okay? Might take you a moment to expand that, but that's what you get for the first two terms. And now we can elaborate on what the components of this become. M gamma becomes m plus 1/2 mv squared plus dot dot dot. M gamma vi becomes mvi plus terms of order vi cubed. Okay? This is just taking this expression right here and plugging it in for gamma. That's all I'm doing. Okay? Now, what is that?
Kinetic energy.
What is that?
Momentum.
What is that?
Mass.
Constant.
Restless.
This is the contribution to the kinetic energy, but it's just involving the mass. It doesn't involve motion. Okay? We call this the rest mass energy.
This is a c squared then?
This is, of course, thank you, this is, of course, the root of the famous E equals mc squared, which, of course, is an expression that only holds in the rest frame of a particle. If a particle is moving, this entire sum represents its energy. In fact, we can define this as the relativistic energy of a particle. So it's the rest mass energy plus the traditional kinetic energy plus higher order corrections. This expression here is defined as the relativistic momentum. Okay? So, when you took relativity, or when you studied relativity in modern physics or other classes, these are quantities that you probably worked with a lot because this is the three-dimensional sort of version of things. You separate energy and momentum. Of course, in this class, we're just going to lump them into a single vector. Boom. Okay, this is a lot more elegant to work with. But if you want to interpret things in terms of energy and momentum, you do so like this. Okay? Now, this is a course in relativity, right? Yeah? So this is a stupid label. I should just call that the energy and the momentum. Of course they're relativistic. This is a relativity course. Okay? So I'm just saying I won't carry around that relativity subscript. All right. Now, so another way that we can say this is that this is the energy and this is the momentum, the relativistic forms. Yes?
What happens to potential energy?
Potential energy is going to be a very different part of the story. In this class, we're actually not going to be concerned with potential energy directly because the interaction we're going to fashion is not the interaction between two objects and the fields they create, but rather the interaction between an object and the geometry that's created by the mass around. But you can certainly integrate potential energy into this story if you need to. Of course, that's part of the dynamics. And we're not even going to go F equals ma on this version of the story. So just bear with me and let me take this where it's going to go. Yes?
So for the momentum vector, does that mean energy is almost like a momentum through the time-like coordinate?
Yeah, you can, no, that's exactly what you can think of. So the momentum for vector has this time-like component, which is the energy, and these space-like components, which are the relativistic momentum.
Cool.
Okay? And just to remind you, P is not mv, it's gamma mv. This is the relativistic momentum, just like that's the relativistic energy. Okay? Now let's very quickly investigate P mu. Well, this should be pretty easy because that's just m squared u mu, which comes out to be, of course, Russ!
I think you turned them off.
You didn't mute him.
Oh man, I did. Did I mute it?
Wait, it's really quiet.
I can't hear anything. Hold on. Say it again.
Oh, hi, I'm here.
What's this equal to?
Oh, that's equal to negative m squared.
Thank you. Okay. Now, this is one way of evaluating it, but another way of evaluating it is saying, okay, P mu vector is this, P mu dual vector is this with a minus in front of the E. So another way of writing what should be the same value is negative E squared plus P dot P, or just P squared. Go ahead.
So, for massless particles, how is the
Massless particles might not play into this. Well, just hang on. I'm going to talk about massless particles in just a second, okay? This expression, which is normally written as E squared equals P squared plus M squared, and if I actually want to replace, or if I actually want to put back into C's, it looks like this. This expression is called the mass shell condition. This is an expression we used quite a bit in my particle physics course. Okay? And this expression is basically just a relation between the energy and the momentum in any reference frame with respect to the mass of a particle. And it comes from just squaring the form momentum, defined either this way or this way. They're the same definition. Okay? Now, if we investigate the different possible signs of this, what we find is that if m squared is positive, then p mu is negative. This also implies that ds squared is negative, which means this is moving along a time-like path. Okay? And one way of thinking of it is a time-like path is any path which wanders into the future light cone, including just only evolving in time and not moving in space at all. So these are called time-like paths. These paths are obviously the paths that are followed by things which are moving slower than the speed of light. But that's, of course, what this says. So if the square of the form momentum is negative, that means the mass squared is positive. That's just using this relationship. Okay? But if something has its mass squared being positive, that first of all implies that ds squared is negative, which indicates that it's a time-like path. So actual physical objects move on time-like paths. Now, this, yeah.
So why does it imply ds squared is negative? M squared is positive. Why does that imply ds squared?
Let me see. Oh, I don't think I have any hints drawn here. No. Okay. So let me see if, I'm going to have to think about that because, well, okay, so one of the things we can do is we can say, you know, this is using this result. This result, parameterized by tau, is only viable if we're traveling less than the speed of light, which of course means that ds squared is less than 0. Actually, that's one way to say it is, if you're traveling less than the speed of light, ds squared is less than 0. I mean, remember, ds squared, maybe this is a better way to argue it, is dt squared minus dt squared plus dx squared plus dy squared plus dz squared, okay? If you're trying, and c sits there, but that's squared, okay? Let's imagine what sign ds squared has for something which is traveling slower than the speed of light. Well, one aspect of traveling slower than the speed of light is being at rest, so all this is 0. Then ds squared is negative.
I like
Okay.
that, yeah.
Right? Okay, so then we have the possibility that it's equal to 0. But if it's equal to 0, what does that tell me about m squared? M squared is 0. What does that tell me about ds squared? It's equal to 0. This is what we call light-like. That is, this is the path that light must take. Okay? Which again will follow from this expression. If I restore the c. Okay? If you're moving at dx dt equals c, and your dy and your dz are 0, then you can plug that in here and ds squared will be 0. Okay? That might seem weird. The vectors are non-zero in length, but the ds squared is 0 for vectors. They're also called null. All right? And then last but not least, if the square of the four momentum is greater than 0, this actually implies that m squared is less than 0, which of course implies that ds squared is greater than 0, which is what we call space-like. And that's a path like this. Okay? This, of course, corresponds to the motion of something which is tachyonic, something that can move faster than the speed of light, but those things don't technically exist in the context of everything being based on a field theory. So don't worry about space-like paths. We won't encounter them. Yes?
Wouldn't that imply that those would have complex mass?
That's what I.
Yeah. That's another way to think about it. But don't even think about that. Don't even get too barred up in this.
Okay.
Because if you remember from particle physics, we define mass as the second derivative of the potential. And what that's actually telling you is that instead of sitting in a stable minimum, you're actually sitting at an unstable maximum.
Okay.
But anyway, that's the backbone of the Higgs mechanism. Okay. So are there any questions about this definition of four momentum? Okay, good. Now, if we wanted to do dynamics, then what we might consider is generalizing Newton's second law, F equals ma, or F equals dp dt, because now we have a p vector. But it turns out that Newton's second law is not the right way to do it. Okay? So what I'm going to do now is I'm going to bust into a topic which is going to be horrible for a little while. And I'm not even going to get through it all today, unfortunately, but we'll get started. And I promise you, this is confusing as crap to me. So it's probably going to be confusing as crap to you, and that's fine. I will put in boxes the final results, which are important. The details of getting to them are not that important, but it's a story I must tell. So, first of all, in this class, we're going to be interested in the source. So remember, in electromagnetism, J is a source. Okay, it's a current. However, in this class, we're not really going to be interested in sources coming from particles, because although a particle does deform space-time, it doesn't do it that much. So what we really want to consider is large collections of stuff, like planets and stars and shit like that, okay? So this is going to lead us to, instead of individual objects, the study of densities. Okay? Now, first of all, you might imagine that what will impact the geometry of space-time is the energy and momentum of a system, because the energy includes the mass of something. So something's mass can deform space-time, but also the energy and momentum that it has can also deform space-time. So somehow energy and momentum, which is just the components of form momentum, this should play the role that J did in Maxwell's equations. Okay, this will be the source. Except it's not just this, it's the density of this. Okay? Now, because I'm not going to be talking about an object, but rather a collection of objects. So now I'm going to get into a very technical definition of entropy, or sorry, density. I can't even say the right words today. And this might be a little ugly, but just bear with me. So, densities. So consider the particle number density, which I'm going to call d little n, which is d big N over dv. Okay? In principle, you can think of this as that expression, where n is the particle number density, n is the number of particles, and v is the volume in which that number of particles is sitting. So hopefully this is a natural definition of density for you guys. The d's are just, I'm going to consider small elements, so it's differentials. This is going to be important later, but this is just the small infinitesimal version of each of these. Okay? So is everybody on board with a number density? It's the number of particles divided by the volume. Right? Okay. You get that, Sophia?
Yeah.
Okay, good. All right, now, this is a scalar. The number of particles is a scalar. You know, 3 particles, 4 particles, that doesn't really matter. This, however, if I'm dealing with a rectangular box, is dx, dy, dz. Is this a scalar? No. If I do a Lorentz transformation, these can change. They can all 3 change, one of them can change, 2 of them can change, but they can change. This product of dx, dy, dz, what the hell is that? I don't know. Okay? So we're going to have to work this out. So here we go. We are first of all going to define the rest frame density as the number of particles in the volume which is at rest. So what we have in mind is the following. The x rest, dy rest, dz rest, and then we're going to have a bunch of particles, which might be moving around. Okay? But when I say rest, what I mean is that this frame has an overall motion of the particles of 0. They're randomly moving, but they're not net moving in any given direction. Okay? So this is the density when the volume in question is at rest with respect to the particles. Okay? So here we go. Let's consider boosting along the x direction by negative v. Okay? So if we boost along x by negative v, then what we find is that d eta, sorry, am I going to call it, I think I'm calling this eta, hold on. Yeah. So in this case, I'm going to call this d eta to differentiate it from that. D eta. So the relativistic version of this is d eta instead of dn. Okay? Then d eta is going to go to d eta prime, which is dn over 1 over gamma dx, dy, dz. Because if you think about it, the only thing that transforms in this expression is dx. And what dx picks up is a factor of 1 over gamma. If you don't remember that, that's fine. Don't worry about it. Okay? But that's basically the length contraction formula. You know, dx goes to dx prime, which is 1 over gamma, 1 over 2 dx. Okay? So this, of course, is gamma dn, because the 1 over gamma in the denominator just brings the gamma upstairs. But we can say that's gamma d eta. Oh, sorry. No, it's gamma dn over dv. My bad. So I just pulled the gamma to the numerator, it's dn over dv, but dn over dv was the original d eta. Okay? This is larger than the d eta that I started with, but that should make sense. Because if I boost along the x direction, the x direction of this box is going to contract, which means the box is going to get smaller. But you have the same number of particles in it, so the density is going to go up. Does that make sense? And that's what we're seeing. Gamma is always greater than or equal to 1. So this result is larger than d eta. Okay? Now, if we take d eta to be d eta at rest, then this is just saying that d eta prime is gamma times d eta at rest. Okay? Now, d eta is clearly not a scalar. Notice, in this definition, d eta is a scalar because this is a scalar and this is just a volume. And in Galilean relativity, a volume doesn't change. You can rotate it, you can move with respect to it, that won't change the volume. Here, though, the volume changed. So the d eta is not acting like a scalar. Is it acting like a vector?
Sure.
Well, I mean, what does it need if it's going to be a vector? It needs 4 components, and this is just a number. So it's acting like, any takers?
I think it's acting like the Timelike component of a vector.
Ross.
Sorry.
That's okay. Yeah, this is actually acting like the component of a vector. So maybe in a relativistic setting, the particle number density should actually be represented not by a number as it is in the non-relativistic case, but instead by a vector.
It's the time-like component because it's not invariant under a boost.
Yeah. Okay? Well, it's not invariant under any boost. Space-like parts can be invariant under a boost that's acting on the other spatial directions.
Okay.
Yeah. Okay, so here we go. Without any further ado, the density vector, which I'm now going to transmit to a capital N, is going to be defined as the rest density times the 4 vector velocity. Okay? Where this thing, and this is going to be odd, is dn over the rest volume. And we're going to take this to be just a constant, a number. I know that seems odd, because shouldn't that be dx, dy, dz, and then shouldn't this transform? No, I'm going to leave that as just a quantity. It's unique because it's the density in the rest frame. It's the only density that's actually unique, because any motion with respect to that could change the value to anything you want. But you could say the density in the rest frame has a unique value. So we're taking that as a invariant quantity. We're always going to have dn rest, or dA to rest. But here's where we're going to get the vector, the rest of the vector. Okay? So what's going to happen is, now we just take this and multiply it by the components of the 4 velocity. So this is going to be d eta rest times gamma, and then d eta rest times gamma vi, okay? Which we can define more generally as d eta and vi d eta. Okay?
Hey, Alex, you have a question.
Oh, sorry, go ahead.
Are we ever going to have to deal with a time where the volume in the rest frame is changing? Like, the entire thing is expanding?
No. So this is not, we're not dealing with the dynamics of a system saying, I'm going to define the system to be everything that's here, and, oh, it's expanded like a star. No. This is a well-defined coordinate volume.
Okay,
This is not an object, this is just a choice of the coordinates.
got it.
But this thing changes size if you boost. That's what's tricky about it. Okay? Normally this wouldn't happen in Galilean relativity. So we're not talking about the actual size of something. That can definitely change things. I'm just talking about a coordinate volume.
Okay.
Yeah. Okay? So let's just check first and foremost what d n mu in the rest frame looks like. And Paul.
dn in the rest frame,
Yep.
I guess that there's a gamma involved.
It's right there. So
Yeah.
what's gamma in the rest frame?
1.
1. What's v in the rest frame?
Also, wait, d in the rest frame or v?
So if you're in the rest frame, what is vi?
Oh, 0.
It's 0.
Sorry, I thought you said d.
Well, at least this makes sense. If we're in the rest frame, the 4-component particle density is just the d eta rest and then 0. Okay? Now, again, this is a pain, and I understand, but we're about to extend. Yeah, go ahead.
What is u the velocity of?
U is it's basically describing the motion with respect to the original defined volume. So if you're at rest with respect to the originally defined volume, then u mu is just 1, 0. If you're moving, then it's gamma, gamma vi. Does that make sense?
Is it the motion of like the mass inside of something?
No, it's just, so if I define this coordinate volume, and it's in the rest frame S, which I might call S rest. So this box sits at rest. Okay, so this is a region of space, and now I want to consider what does it look like to me, because I'm now in S, which is moving with respect to it. The u4 vector velocity is basically my 4 vector velocity. Okay? Now, again, I'm going to repeat this essentially, but here's the important takeaway. We started out with a scalar dn. Actually, sorry, I really and truthfully should not do that. I should say I started out with this scalar. And you'll understand why in a minute. In order to make it a density, we had to promote the scalar quantity to a vector quantity. Okay? And again, the reason for that is because normally to make a density you have to divide by volume, but the volume transforms. So then you have to recognize that what you're constructing is not actually a scalar, but it's a scalar divided by something which is transformed. Oh, it's more like a component of a vector, but we have to fill out the rest of the vector. Okay? Now, oh, we're going to run out of time. That's fine. So, let me give you another way to think about this. So, essentially, when you're in 3 dimensions and you talk about a density, you're basically taking something that's present and dividing by the volume that it's in, right? In 3 dimensions, a volume is really just the size of it. That's it. However, what if I'm in 3 dimensions and I'm considering the density of a 2-dimensional system? That is, I'm considering a surface and I'm talking about the number of particles per unit area. To specify an area in 1 degree or 1 dimension higher space, is it enough just to give the size of this? No, what else do I have to give? Say it again? Yeah, I have to tell you what orientation this takes. We don't have to do that if it's a volume in 3 dimensions, but if it's an area in 3 dimensions, you have to specify the orientation. Does that make sense? So you all are aware that the area is a vector, which is described by a vector orthonormal to the surface, and then it's just that little differential area is the size of the vector. Okay. So that's the way the story plays out if you're dealing with a 2-dimensional surface in 3 dimensions. We good? Sorry for yelling. This is important. Wake up. Now, we are working with a 3-dimensional volume. Do we have to worry about how this is oriented? Hell yes, because this lives in 4 dimensions. 3-dimensional volumes in 4 dimensions have a size and an orientation. So there is a vector associated with this volume in the same sense that there's a vector associated with this area. And it has to do with this thing being defined in 1 higher dimension. Okay? There's a few more details on this. There's an example of finding the area vector in 3 dimensions, but I'm not going to go over that right now. Okay, you can look it up in my notes. It's not that important. But if this is confusing to you, have a look at my notes. Okay. So, what we have come up with is the following. First of all, going back to non-relativistic situations, if I have that the number of particles can be written as the density times the volume, okay? That is the good old non-relativistic density times volume is the number of things. This should be obvious, okay? In the relativistic story, the way this plays out is that the number of objects, that's what dn is, the number of objects is the density, this is the number density, which of course is a 4-vector. We had to promote it to a 4-vector, times eta mu dv, which is the volume. That is the size of the volume, a 3-dimensional volume is what I'm talking about here, and a vector, a 4-component vector, which is basically normal to the volume. Okay?
And this data is different than the metric data, correct?
Yeah. So this is, I mean, the metric data has 2 indices. Okay? This, of course, forms a scalar, because I'm taking a vector and a dual vector and I'm contracting them. Okay? Actually, screw it. I'm just going to go through this real quick, and then we'll end at the end of this page, and next time we'll pick it up. I want to motivate this, because this might not be obvious. So let me do the 2-dimensional example. So first of all, in 3D, a surface is defined by basically a function of x, y, and z, which is equal to 0. Okay? So if I coordinatize my 3-dimensional space by x, y, and z, and then I just basically give you a function of x, y, and z, which is equal to 0, this basically defines a 2-dimensional surface. Let me give you an example. If I use the function x squared plus y squared plus z squared minus r squared equals 0, does this define a surface? Well, let me give you a hint. What surface? It's the surface of a 2-sphere. That is, this is all the points in x, y, and z, which are the same distance from the origin. That distance is r. Okay? But if I just move this like that, this is of this form. Okay? So this is the more sacred form. You know, don't worry about that it's got to be equal to r squared or something like that. Okay? Now, dA, the area vector associated with this is df dx I hat plus df dy j hat plus df dz k hat. Okay? Well, if I take the derivatives of this function, this is the function. If I take the derivatives of the function, I get 2x I hat plus 2y j hat plus 2z k hat. Okay? Now here's the cool part. If I take the x and y and z, which satisfy this expression, this is just going to amount to r times r hat. That is, it is exactly what you think of if you have a 2-sphere. This is just the surface, it's not the volume. The 2-dimensional surface is the subspace of 3 dimensions, and you know that perpendicular to that is the r hat direction. And that's what we just found. Okay? So this is again illustrating that in order to define the size of something, or a 2-dimensional subspace of 3 dimensions requires a vector. This is how you find the vector. Okay? We have to deal with a three-dimensional volume embedded in 4 dimensions. So you might think that it would be composed of a vector, except for one thing. What are the components? d by dx, d by dy, d by dz, those are components of what kind of vector? We talked about this last time.
Can I answer?
Go ahead, Ross.
A dual vector.
They're components of a dual vector. Remember how we said that d by dx mu is just what we would call d mu? Yeah, these are the components of a dual vector. So the volume in 4 dimensions, or the area in 2 dimensions, is described by not a vector, but a dual vector. And that's exactly what I have here. Because this has a lower subscript. Okay, or it has a subscript, not a superscript. Okay? Which is perfect because this dual vector combines with this vector to make a scalar. All right? Now one quick observation and we'll get out of here. And this will just open the door to what we're going to talk about on Tuesday. This will literally just take a second. If we try to extend this story to the momentum density, okay, then trying to play this out basically goes as follows. If I actually want the amount of momentum in the volume, that's the same as here I said this is the amount of particles in the volume, then this has got to be equal to the density times the volume. Okay? So again, this is the volume. This is the momentum density. There's just one difference which should be observed. This is a scalar. The volume is a dual vector, so the density should be a vector. However, here, this is a vector, this is a dual vector, so what does the density have to be? How many, what rank?
Rank 2.
2, 0. This is the energy momentum tensor. The energy momentum tensor is nothing but the density of energy and momentum. And we'll develop that in detail next time. That's it for today.